Okay, so welcome back. So now we are starting fifth lecture. So what topic is covered? Almost about the finite fields and certain basic things. So now I'm going to start another chapter in your book, which is logic. Now I think logic is very old subject. So probably I will show you one slide about brief history, and I'm not going to cover most of the other history you can read anywhere else. But and there are why we should study logic. There are plenty of applications, right from your program checking and verification, right, solving different kind of puzzles, and so developing new kind of algorithms also it helps you. How do you do that? And faulty circuit analysis you can do. Or different kind of applications are there. So basically, it's a very very important topic, and there are different order of logic: zero order logic, first order logic, second order logic, and so on. We are going to look at only two of them: zero order logic, which is also known as propositional logic, and second one is first order logic, which is also known as uh, you know predicate logic. So are you aware of this logic business in some book earlier, high school mathematics? No. Okay. So some book boards may have covered it, by the way. Anyway, so we start with, how many of you have read Rigved? Rigved पढ़ा है? So in Rigved, Mandal 10, there is so there are about more than 10,000 shlokas in Rigved. In Mandal 10, there are different mandals actually. You can call it chapter also. So one of them, so there are three important ones. Suktam. Suktam is a collection of sutra or shloka, right? So there is one which is known as Nasidiya Suktam, and actually this is about origin of universe, how our universe came. By the way, some of you might, I don't know whether you might, know you are a bit young, but maybe 20 years, 25 years back, there was a popular TV serial, Bharat Ek Khoj. Have you seen any of them? Based on that book by Jawaharlal Nehru, right? So they have, so whenever this serial starts, this shlok they read. Nasada Sinyo, Nasidrajo, Novayamo Proyata. So actually, what is the meaning of all this? The first time in the origin, so they say that that in the beginning nothing was there, and from that not nothing, all kind of things are there. It's an interesting thing. So I think I leave it to you to analyze this shloka, and there are 7 of them actually. So probably you can read all of them, which is about the creation of this universe. And here, first time they have used these kind of things: A, not A, A and not A, A and not A, and not A, all kind of compositions. So what does that mean? So this is something first time in the human history they have used these kind of logical thinking, and about, so there is a, I mean, this is from Rigved, and after that there were so many people who have worked. I've only showed you the slide of Indian things. So, and out of them, so Panini has done something, Gautama is there, Buddha logic, Jain logic. In fact, Nagarjun is very, very close to what is the modern logic, what you say. And then, you can find a whole history of this Wikipedia timeline of, so Ptolemy and other Aristotle and so on and so forth, all the Western philosophers, right? But of course, there is a lot of history about Indian things in the beginning. So those who are really interested in reading more about this logic business, I mean, the history is always important. You should know how things are developed, Anyway, so let me start with first thing, which is proposition logic or zero order logic. So there will be certain propositions. So sort of we are always making some statement, right? So each of us making some statement. I say something, you say something, and so on. So whatever in whatever language, so suppose we are speaking English and we are making some statements, so we can assign some value to it, whether it is true or false, a true false system. So propositional logic is about true and false. Some statement you make, it could be true or it could be false. But in such a simple system also, there are problems. For example, if I ask each of you, take a piece of paper and on one side of the paper write down the statement on the other side of the paper is true. Reverse the paper and write down the statement on the other side of the paper is false. Now, can you conclude the logical conclusion? You start with one side, assume it is true, and you arrive in a contradiction, right? Either side. Do you understand what I mean? You can try on yourself, right? Take a piece of paper, write down on the one side, the statement on the other side of the paper is true. Reverse it, the statement on the other side of the paper is false. Assume one of them is true, then you arrive at a contradiction immediately, right? It's the beauty of logic, right? So basically, such kind of things are there, right? So basically, uh, so we are going to focus on this propositional logic, and where are the applications? Of course, I can cover a lot of them. We can talk only about applications, specifications of hardware and software, designing computer circuits, constructing computer programs, verifying the correctness of programs, Boolean searches. I think on Google many times when you use, something and you use and operation, right, in between, right? So that is in Boolean searches, inference and decision making, and solving bunch of logic puzzles. So knights and knaves and muddy children, these are the famous. There are many more actually. So I don't have not listed all of them, but these are some of the applications of propositional logic, right? So very important topic. If a circuit is given, you want to verify whether it is true or false. I mean, you want to check the correctness of the circuit. If it's a faulty circuit, whether you want to check that or not, right? So you can use these logical inferences to calculate the final thing. So basically, these are some of the applications. So I invite you to look at some of these applications on your own. Google is all yours, right? Search about some applications. So maybe a circuit, you can see that propositional logic, we can also correspond to circuit for each of them. Circuit is either, see, if you make a simple circuit and so some battery and so on and so forth, right? So if, and there is a switch. If switch is on, switch could be in two states, on and off. It's something like true and false, 0 or 1, right? Binary system, and which will convert everything, right? So there are a couple of circuits involved, so two circuits in parallel and so on, the simple circuits, all kind of combinations can be made, right? So that is a general thinking about applications in circuits. So let me start with this beautiful thing. So we call something, so propositional logic deals with propositions. What are propositions? Let me see. Delhi is capital of Canada. So it is true or false? False. So we can assign this value F, right? Second, 1 plus 1 is equal to 2. Is it true or false? So now you see the beauty, right? In what sense you are talking about? For the common people, 1 plus 1 is 2. So then it is true. When we are in digital model 2, it is 0, right? So of course. Two plus two is equal to 3. Is it true or false? It is true when you do the modulo. Which operation you need to do? And 2 plus 2 is equal to 3 for what modulo operation? Do you think there will be an operation? No such thing anyway. So it is false anyway. So these are propositions. You are making a statement which is either true or false. Now, if I write down another thing, what time is it? So, is this a proposition? No. It's not a declarative statement, right? So, it's not a proposition. Another example, if I take x plus 1 is equal to 2, is it a proposition? No, because, okay. So, these propositions we denote it by small letters, like small letters of English like P, Q, R, S, and so on. So these statements we denoted by these letters, small letters P or right, and truth value is denoted by true or false, T or F. Okay. So for example, this is statement I can call it P, and this is true, right? Or I can call it this is a Q, this is R, this is S, but this is not a proposition anyway. So PQR, these are, all the propositions we denoted by small letters of English, right? PQR. And capital T and capital F denotes whether it is true or false. Okay. So if P is a proposition, then negation of P is also a kind of proposition, right? So sometimes we also denote it by P bar. Okay. So this means it is not the case that P, right? It's a negation. So for example, if I say that P is the statement, today is Friday, is it true or false? This statement is true. Today is Friday anyway. And negation of P is today is not Friday. Okay. So basically, this is really very simple thing. Most of the logic things are very simple. I mean, the proposition logic is very, very easy. And I think the first order logic, the predicate logic is also very easy. You will see it's a very easy thing. And when you go a bit higher, it becomes beautiful, right? So more and more beauty will come. So this is less beautiful, I would say. So most of these, truth values. So we can actually, what is known as truth table, you might have heard. So we can describe some of these things with this truth table. So what are these truth tables? By the way, the other instructor, Professor Manoj Raut, is expert in this area. He has done PhD in logic, right? So truth table for negation of P. If P is there, the negation of P. If P is true, the negation of P is false. If P is false, negation of P is true. This is a simple truth table, right? P and negation of P. I'm just describing. So all these, I'm now going to describe different kind of operations on these propositions right? And then we can check whether those operations, truth table, what is the truth value, right? Could be true and false, right? Depending upon what individual thinks, whether it is true or false, I can come up with what is the whole conclusion. Then we have another one, which is known as P meet Q or P conjunction Q. So this is a proposition. Normally we call it P and Q. P and Q. So I can describe this also by a table. P, Q, P and Q. If this is true, then true. If this is true, Q is false, then false. And if this is false, this is true, then false. And if this is false, then this is also false. For example, if P is a statement proposition saying that today is Friday, and suppose Q is a proposition, it is raining today. Right? Then P and Q will be today is Friday and it is raining today. So many times, actually, all these statements in English language, for example, you convert into these, these kind of logical, variables or whatever you call. So in this, and then you can simplify the analysis, so that's why it's very, very, so I think one can give you a lot of exercise like these are the English sentences, convert correspondingly, write down the corresponding PQ values and so on, whatever the operation you do. Or if this kind of, expression is given to you, say P union Q, P join Q, meet Q bar, what will be the corresponding English sentence? If P and Q and R is given to you, right? Those kind of conversions are quite useful. So actually, when we are doing some logical conclusion, doing it in the English language will be difficult. But if you have these kind of variables involved, right? So you can arrive at a inference or something, some logical conclusion to the final thing, right? It's easy when you convert everything in this form. Okay. The next one is disjunction or join. P join Q. We also call it P or Q, right? So truth table is P, Q, P join Q. This is true, then P join Q is true. If this is true, this is false, then true. If this is false, this is true, then this is true. If this is false, then this is false. So I think most of these things you might be, I don't know, where do you read? Digital logic. Yeah. So you see the circuits are beautiful in this logic, right? Okay. The fourth one is exclusive OR. We call it as P exclusive OR Q. So actually you need to keep in mind that this is true when exactly one of them is true and is false otherwise. Right? P, Q, P exclusive for Q. This is true, then this is. Now you can clearly see that exclusive OR business, you already know it is kind of integer modulo 2, right? Can you see that? That can, if this is true, this is false, then this is true. If this is false, this is true. This is true. If this is false, then this is false. Right? So exclusive OR operation is just like, you can think like this, 1 plus 1 is 0, right? 1 plus 0 is 1, 0 plus 1 is 1, and 0 plus 0 is 0. Right? Correct? That your Z2 business. So Z2 is so important, right? Okay, so these four were quite easy. Negation of P, then P meet Q, or P and Q, P or Q, or P join Q, we also call it, and then P exclusive for Q. These are the basic things, right? Between two statements, we can do this. Now, there are some conditional statements, which are very, very beautiful, right? So conditional statements. Suppose P and Q are two propositional statements, right? Two propositions. Then P implies Q means what? This is a proposition. If P, then Q. If P, then Q, right? Now, what we can say about true and false? So this is, you can think of a hypothesis, and this is the conclusion, right? If P is true, then what about Q? So basically, this whole thing is false when P is true and Q is false. So this statement, or this proposition P implies Q, right, is false when P is true and Q is false, right? And this is true otherwise. Right? So we can create a table P, Q, P implies Q. This true, then this is true. If P is true implies Q is true, then the whole thing is true. This is true, this is false, then this is false. This is false, this is true, then this is true. If this is false, then this is true. So these truth tables are easy. Once you construct the truth table, you can understand the whole logic behind it, what is happening, right? So always, whenever you are in trouble, actually you will see that these truth tables are very important in establishing different kind of equivalences between different propositions, right? Some collection of propositions are there doing some operations, another collection of propositions with some operations. You can make the truth table and check, right? If the truth tables are same, then these two things are same, right? Okay. So when I say, so suppose there are three variables P, Q, R, and there is one expression on one side, and there is some other expression on the other side using different operations. Then you know that with PQR can take values true or false, T or F, right? And you can make the final expression, whatever it is coming, true or false, right? Similarly, on the other side, you can again assign P and Q R as true and false. So whatever the possible things or expressions, whether it is true or false, you can calculate. If the truth tables are matching, then both the expressions are same. So that is easy to show. So here, I mean, this conditional thing we also call if P then Q, if P comma Q, P is sufficient for Q, Q if P, Q when P, a necessary condition for P is Q, right? P only if Q, Q whenever P, all these English variations you can use, right? So that's okay. Q is necessary for P, Q follows from P, all kind of things. Okay, so then we have another one. Converse, contrapositive, and inverse. What is the meaning of these three? Q implies P is converse of P implies Q. P implies Q, the converse is Q implies P. Fine? The contrapositive of P implies Q is negation of Q implies negation of P. By the way, you might have seen this kind of stuff we have used in one of the proof. Remember? When we were showing integer modulo n is field if and only if n is prime, we assume that P is prime, we arrived at thing, then we took the negation, we actually took this contrapositive thing, right? So we have used that trick earlier. Then biconditional. This is pretty important. Biconditional. P if and only if Q. So basically both sides are same. This is the proposition. So we can make the truth table actually here. P, Q, P if and only if Q. I don't like this. Okay, if this is true, then this is true. This is true, this is false, then this is false. This is false, this is true, then this is false. And if this is false, then this is true. Right. If and only if it is very clear. Now these are all still simple. So we have done some basic things, right? We talked about biconventional, converse, contrapositive, inverse, and conditional statement, and then these basic 4, 5, 6, 7, 8, 9. We've talked about 9 basic concepts. Now we can look at some compound propositions. Okay, it's a bit more complex or having more variables. So now we are going to look at compound propositions. So we have P join negation of Q implies P. I hope it is clear. P join negation of P, negation of Q implies P meet Q. So what I can do, I can actually make a truth table one by one. P, Q, negation of Q, because we need negation of Q. P join negation of Q. P meet Q. And finally, P join negation of Q implies P. Right. So I think you can also try to fill this table. If P is true, Q is true, negation of Q will be false. Then this thing will be true, this thing will be true, this thing will be true. If this is true, this is false, this is true, this is true, this is false, this is false. If this is false, this is true, this is false, this is false, this is false, whole thing is true. This is false, this is false, true, true, false, false. It's just easy calculation, right? Just keep on doing, or whatever is the basic 9 basic things you read, right? Keep on applying, and finally you arrive at the conclusion. Okay, now one thing, when we are evaluating these kind of expressions, so I think in programming you might have, you remember, which operation to use first, right? Or some sort of, if there are different operations we have to do. I mean, for example, in the basic math, you know that addition, multiplication, and simple expression is there, right? So which expression to use first so that is very, very important. So we are going to tell you the precedence for the logical operations. Operator and precedence. This we need to do first precedence. This is second. Meet, join is third. This is fourth. And if and only if is fifth. This is the way you need to evaluate the logical operations. Okay, now we are ready to give you what is known as propositional equivalence or logical equivalence. Before that, I'm going to tell you what is known as tautology. A compound proposition that is always true. Always true. No matter what the truth values of the propositions that occur in it is called tautology. Example, P join negation of P. This is tautology. How? We can see the. So if we make a table, P, negation of P, P join, negation of P, you can see that this is true, this is false, this is true, this is false, this is true, this is true. Right? So this is a tautology. No matter whatever is coming individual, final output is always true. In fact, so if a compound statement is always true, it is called tautology, and if it is always false, then it is called as contradiction. So here is an example for that also. P meet negation of P. So this is always false, no matter what you do. So tautology and contradiction. A compound proposition that is neither tautology nor a contradiction is called contingency. Okay. So, okay. Definition is okay, but I am skipping that. Okay, so I think these are the basic important things. Now let us do 1 or 2 examples of logical equivalence and we are done. with the propositional logic. It's very simple thing, right? So let us do up. We need to logic. Okay, so we are back. Logical equivalence. So two basically compound propositions P and Q are logically equivalent. We call it, we denote it by that P is logically equivalent to Q, or we denote it like this: P. Two compound propositions means there are combinations of variables in it, right? Two compound propositions are logically equivalent if P, if and only if Q is a tautology. If this is a tautology, then they are equivalent. So let us see. And I think the last time I did a mistake here, so I want you to be careful observation, because when you write this true, false, sometimes you write false in place of true and so on, right? So just observe. Okay. So we want to show that negation of P will not allow, huh? Negation of P join Q and negation of P, negation of Q are logically equivalent. Now, do you think that this is negation of P, something like have you heard of this De Morgan's law, right? So very good. So we need to prove De Morgan's law basically, essentially, right? So what I'm going to do, I'm going to make a truth table P, Q, P join Q, negation of P join Q, negation of P, negation of Q, negation of P join negation of Q. Just make sure that I am writing it correctly. I remember last time I have done a mistake. Anyway, this is true, then this is true. And what about this? False. Negation of P will be false, false, false. If this is true, this is false, then this is true, this is false, this is false, this is true, this is false. This is false, this is true, this is true, false. Huh? Which one there is a mistake, This one? This one? This one? Okay, tell me here. Last column? This one? This is negation of Q. Okay. See? Fine. Okay, fine. So this is false, this is true, this is false, this is false, 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 true, 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 and true. Now you can clearly see that We wanted to establish equivalence between this and this, right? And these columns are matching, right? So they are equivalent, right? Okay. So I think this is really easy. Now I can show you the tables rather than doing it, writing it. Okay, we go here. So these are all notes I have already written. I probably you are getting all these notes. So yes, so other examples are like this. Maybe I can show you to F5 screen mode. So you can see that we have other example. P implies Q is logically equivalent to negation of P, join Q. Again, you can fill the table and you can observe the equivalence, right? This is easy. This is a little bit lengthy, the distributive law. So I think all these things you know from the digital logic course, right? So everything is similar. You just use these T2, I mean, true, false kind of combination and see the things are same. In general, so as an exercise, even if you have done probably one or two you can do, right? Identify any of these laws, identity laws, domination laws, idempotent laws, double negation law, all these laws are there which you can verify using this truth table business, right? So very easy, any high school person can do it. So you can do it. There are some more, right? Commutative law, associative law, distributive law, De Morgan's law, absorption law, negation law. So many. So it's easy to ask you, how much time is there? Should we take a quiz? Because few people. Yeah, so I think that's all about the proposition logic. Everything is done. So I'm saying if time is there, then we can take a quiz, or these people are not there, right? Oh, sorry. Okay. Just tell them next time it will not be the case, right? So, okay. So this is all about proposition logic. Next time we will look at the predicate logic. It's very simple, right? And then we are done. And then some no, normal forms of the logic. That's all.